Oh, it's great to have Dmitrii Pirozhkov now from Paris, who will talk about stably indecomposable varieties.
Hello. I thank the organizer for inviting me to give a talk in the seminar, and I will speak about this certain study of indecomposability properties of derived categories of varieties. So to state the stage, I'll start with so I will work with varieties over some field, and I guess for simplicity it will be complex numbers, but I think that's not really required in most of the places. So if I have some, and when I say variety, I mean connected reducible variety over that field. Over, let's say, C. So if I have a variety, then I can form its, d of x, which will be, which for me will be a notation for a bounded derived category of coherent sheaves. So it's a small category. One way to study derived categories of varieties is by looking for semiorthogonal decompositions. So we have this notion of semiorthogonal decompositions that I will remind a little bit later. Semiorthogonal decompositions, they allow us to kind of describe this derived category d of x, which is a triangulated category, in terms of kind of smaller components, which in good situations they are easier to understand, or maybe sometimes the components themselves are interesting and unusual. But in any case, for certain varieties x, we can prove that there are just no semiorthogonal decompositions available, so you cannot split this particular category into smaller pieces. So some x have indecomposable derived categories. And I guess the main criterion that we have is a result by Kawatani and Takawa. From 2011. They proved a little bit more than this, but I stated in the form that's often occurs. If X has a globally generated canonical bundle, then d of x has no non-trivial semiorthogonal decompositions. In particular, this includes curves of positive genus, Calabi-Yau varieties, and many other examples. So one thing that's we would like to kind of use varieties for which we know the indecomposability to study possible semiorthogonal decompositions of some related varieties. For example, we can ask the following question. This is just one possible question that we may think about. So if x, let me do it. Okay, sorry. If y has indecomposable derived category, x any smooth proper variety. So do all semiorthogonal decompositions of the derived category of x times y, of just the product, do they all come in a certain sense from d of x? So if y has a decomposable derived category, is it true that whenever we decompose the derived category of the product, what we are doing is that we are just choosing the decomposition for the first component? So that's a natural question. And the problem is I don't know the answer to this question. But I will give some stronger condition on y that's not just indecomposable derived category that will imply, among other things, a positive answer to a question like this. But under stronger condition on y, the answer is positive. What exactly is a stronger condition is the main subject of my talk, as well as giving examples of varieties y with this property. Okay, so right, so let me start a new section. I want to start discussing stably, semiorthogonally. This is a bit of long term, semiorthogonally indecomposable varieties. And since it's so long in this talk, I will generally omit the word semiorthogonally and just say stably indecomposable variety. Okay, so before I give this condition, I need to recall two definitions. First, I would like to explicitly say what is a semiorthogonal decomposition of a triangulated category T. Is a pair A, B of strictly full subcategories of T, such that two conditions hold. The first one is that this pair A and B together generate T, in the sense that the smallest triangulated category containing both A and B coincides with T. And second is that if for any object A in the first component and any object B in the second component, there are no maps from B to A. Sorry, and I guess I didn't say, but when I speak about subcategories of triangulated categories in my talk, this automatically means that they are triangulated subcategories. So they are closed under cones and sheaves. Right. So this is just a standard definition of a semiorthogonal decomposition. And the second definition that I would like to recall is the notion of linearity of semiorthogonal decompositions over some kind of a base. So let's let pi be a map from like x to y. And let's say this is a map between smooth proper varieties. these conditions of smoothness and properness may be relaxed since we are just given the definition, but for simplicity, I will stick with these conditions. So, and suppose that we have a semiorthogonal decomposition of d of x. Then we say this semiorthogonal decomposition is pi linear, or sometimes I will just say y linear, since it's kind of since pi is a map to y. If for any object A in the first component of the decomposition and any f in d of y, the product, the tensor product A tensor f lies in A. So the decomposition is linear if one or equivalently both of its components are closed under multiple tensor products by, sorry, I guess I should write by pullback. Since f is an object on y, I can take its pullback, which it will be an object in the derived category of x, and I can consider this tensor product. And the condition is that the decomposition is linear if it is closed under this operation. Right. Now let me give the main definition of this talk. So I say that y is stably indecomposable if for any morphism pi from some x to y with x smooth and proper. So if for any maps from smooth proper varieties into y, any semiorthogonal decomposition of x is y linear. So if for an arbitrary morphism to y, for an arbitrary decomposition of the total space, curly x, each decomposition is automatically has this property of being closed under tensor products for objects from below. Right. Any questions about this definition so far? Okay, if there are no questions, I'll go on.
You wanted to say something about both components of the pullback of F?
I'm not sure I understand the question. Okay. So can you ask the question again? Sorry.
No, just ignore. I had the impression that you were going to make a comment, but never mind.
Okay. Right. Okay. So this is the definition, and before going deeper into a study of this notion, let me try to see if we can copy it.
Sorry, may I ask a question?
Sure. Go ahead.
Maybe mention this. In this definition, do you require any thing on this pi?
No, just the total space should be smooth and proper.
Okay, and not need to be flat or something.
No. In particular, it should work for closed embeddings.
I see.
Yeah.
Okay.
Okay. All right. So let me try. Okay. So before I continue, let me just announce I will not prove it at this step since I will need some preliminary discussion. That this notion indeed gives a positive answer to the question that I started with. So if y is stably indecomposable, x is any smooth proper variety, then whenever we have a semiorthogonal decomposition for the product, this implies that there is some decomposition of d of x into components ax, bx, such that this curly a that we have in the product is just a base change of the corresponding component from d of x, where this notation that I'm using just means that as the category curly A, we take pullbacks of all objects from X that land in AX and multiply them by anything pulled back from Y and take the smallest triangulated category containing all these products. So in this sense, any semiorthogonal decomposition of X times Y is induced from a decomposition of X. And again, I don't know if this is true if we just assume that derived category of Y is indecomposable. Maybe it's true and maybe it's simple, but I wasn't able to prove anything without this stronger condition. Okay. Right. So the first thing that I should mention about this definition is that it is not empty, and there are examples for which we can prove this definition, even though it seems extremely strong because it kind of refers to all possible maps from smooth proper varieties into Y and all possible semiorthogonal decompositions. So the theorem is that if Y has a finite Albanese morphism, so the morphism from Y to its Albanese is finite. Then Y is stably indecomposable. Right.
Sorry, I still have a question about stably indecomposable. So if Y is stably indecomposable and X is a finite cover, does it follow that X is indecomposable?
Yes, I will actually state this in a little bit. So if you are, some properties of stable indecomposability are inherited by, for example, some subvarieties. Okay, sorry, I'll do this a little bit later. Any other questions? Okay, so with the definition underway, I would like to move towards the proof of the theorem. And for this, I will need to discuss some properties of stably indecomposable varieties. Or rather, properties of this definition.
Can I ask a question? Stupid
Sure.
question.
Okay.
So if you consider, suppose Y is stably indecomposable, and you consider a trivial decomposition where A is the whole category and B is 0, And
Okay.
then you're saying that the category of the product y times itself is something generated by the outer product. What about the class of the diagonal, for example? Maybe it's something that I don't understand.
So it is known that for the derived category of x times y, this exterior tensor product, as I've written over there, between pullbacks, generates the entire derived category.
Okay,
so, for example, the class of the diagonal in y cross y, y itself, it does not look like a product of two pullbacks. It kind of has something like a resolution. It lies in the span of such objects.
Thank you.
You're welcome. Okay. Right. So, so the first, I would like to state the lemma, which is kind of a sanity check, that if y is stably indecomposable, then it is indecomposable. And this has no non-trivial semiorthogonal decompositions. Since the definition I gave for stable indecomposable was a little bit, it does not look exactly like non-existence of semiorthogonal decompositions. I would like to show you why this is true. All right, so the idea is that if we assume that we have some semiorthogonal decomposition of d of y, let's say we have this assumption, some semiorthogonal decomposition, then we can apply the definition of stable indecomposability, which holds for an arbitrary morphism from a smooth proof variety. Apply main definition to just identity morphism from y to y. So according to the definition I've given, if this decomposition is a decomposition of d of y, then we know that this semiorthogonal decomposition is kind of y linear, in the sense that each component is closed under tensor products with arbitrary pullbacks. But since we are dealing with just identity morphism, this means that A and B, so kind of in other words, are kind of tensor ideals, if you want. Subcategories say that when we take an object in A and multiply it with using tensor product with some arbitrary object of d of y, we still land in A. So in particular, so suppose we have some object A in curly A, and let's say P in Y is a point in the support, in the set theoretical support of this object, which for an object in the derived category is just set theoretic union of supports of cohomology sheaves of this complex. Then we know by assumptions that A tensor skyscraper sheaf is in A. But when we take the tensor product with a skyscraper sheaf, we just get some object that is supported purely on the point P. And one may check that this implies that, in fact, skyscraper sheaf is an object in this category curly A. And the only condition was that this point was inside of the support of some object in curly A. So one consequence of the fact that skyscraper sheaf lies in A is that by this semiorthogonality condition, it means that support of any object in curly B does not contain this point P. So for each point, we have this kind of dichotomy, either the skyscraper sheaf at this point lies in A or it lies in B. And sorry, I guess I'm always forgetting this Y is also connected. Sorry. All right. So, and one may check that this property over here implies that kind of Y splits into a disjoint union of two subsets. All objects in A are supported on one component, B on the other component, and one may check that both of those subsets are actually open. Both Y1, Y2 are open. This follows from semi-continuity of cohomology. So if this semiorthogonality condition was about homes, we know that skyscraper sheaves just lie in some of the components, and one may check that both open subsets are open, so we get a contradiction with the fact that Y is connected unless Y1 or Y2 is empty. And if one of the subsets is empty, it just means that the corresponding component of the semiorthogonal decomposition is 0.
Ask, how do you know in the proof that the skyscraper sits there? It could be a thickening, right, in principle?
Not really, because kind of skyscraper sheaf is a push forward of the structure sheaf of the point. And when we take a product like this is the same by the projection formula as the push forward of A tensor, sorry, of the pullback of A tensor structure sheaf, but where J is the inclusion of the point. Since here we just take the pullback to the closed point, any objects in the derived category of coherent sheaves on the point is direct sum of structure sheaves. So it follows that if this product is always a direct sum of copies of sheaves of a skyscraper. Right. Okay, so at least this was a confirmation that the definition that I gave is meaningful. It implies this nice property. Okay, so now I can give a second lemma, which Arendt suggested some time ago after I stated the definition, that suppose we have a morphism which is finite, and assume that Y is stably indecomposable. Then Y prime is also stably indecomposable. Right. So why is that? Well, let's just look at the definition. So we start with an arbitrary map from X to Y prime. But then we can also consider X as a smooth proper variety over Y because there is this natural morphism F. So we have d of X, which is some semiorthogonal decomposition. We need to show A is closed under products with d of Y prime, in the sense that for an arbitrary object in on the Y prime, we take its pullback to X and multiply by this. But what we know is if we consider this curly X as a variety over Y, we know that A is closed under d of Y. So if we take an object that's not just on Y prime, but in fact on Y, and consider its pullback, then we know that the decomposition that we have over here is Y linear, because Y is assumed to be stably indecomposable. But the pullbacks of objects in d of Y generate d of Y prime. So since f is finite, So I mean, for example, a pullback of an ample line bundle under a finite morphism will be ample, and this implies this property. To make this completely rigorous, one need to say some other words, like we need to consider the largest subcategory in D of y prime of objects, such that multiplication by those objects does not, such that A is closed under the multiplication by those objects, and we need to show that this category is triangulated, contains all the pullback, and so on. But this is all just technical announcement of this reason that just pullbacks from Y generate derived category of Y prime.
Yes, because it's efficient to tensor with structure sheaves, as you did in the previous proof, to check this condition.
Yes. It will be sufficient, and actually this is how the proof of the main theorem works. Okay, right.
Can I ask a question?
Sure.
Can you that relax F to be just like a affine morphism?
I mean, in my definition, I want my varieties to be smooth and proper, so I don't really have affine. But in general, if you want to deal with more general class of varieties, then I guess affine morphism is also fine. I have some generalization of this notion of stable indecomposability, some mild generalization, slightly more categorical than geometric, but it still needs properness. So I'm not sure.
Okay, thanks.
Right. Okay. Right. So one corollary that I would like to mention for the previous lemma is that if we have Y stable indecomposable, and then any smooth proper subvariety of Y is also stably indecomposable. So it follows just because the inclusion morphism of a subvariety into Y, closed embedding is a finite morphism. So the previous argument just shows this. In particular, we can look at the following example. If we take Y to be just a case-free surface with a rational curve, C, which is P1 inside Y, then by this corollary, we know that Y, then we see that Y is not stably indecomposable, even though by this Kawatani-Akawa theorem, we know that D of Y is indecomposable. So the condition that I gave is at least stronger, strictly stronger than the just derived category being indecomposable. So this is just an example to show this. All right. So now I can indicate how the proof of the main theorem goes. So to do this, first I need to give another definition, another standard definition. So a set S of objects in some triangulated category T is a spanning set. if for any object, let's say f in T, we can find some, I don't know, sorry, let this be curly S, and this will be Roman S. So if for any object we can find S such that home from F to S is not 0, and we can also find some S prime such that home from S prime to F is not 0. So kind of a set of objects is called a spanning set if by looking at homes to this, sorry, I guess I'll put a dot over here for simplicity, where here I mean just home, there is some shift of S such that home is not 0. So set is spanning if by looking at homes into it, we can detect 0 objects. Sorry, for any F which is not 0. Otherwise, this is impossible, of course. Okay, so one example of this, that if Y is smooth proper, then the set of skyscraper shapes is spanning in D of Y. Right. So this just means that if you have any non-zero object in the derived category of Y, then there is at least one skyscraper such that there is a non-trivial morphism.
By the main theorem, you mean the statement about the finite Albanese?
Oh, yes, sorry. Main theorem here is the statement that if a variety has finite Albanese morphism, then it is stably indecomposable.
Thank you.
Okay, good. All right. So, okay. So this is the main example, and I want to give a lemma that if A is another example of a spanning set, that will be the crucial observation for the main theorem, that if we have an abelian variety, then besides the skyscrapers, we also have just line bundles of degree 0. And I claim that this set of objects is spanning. Sorry, I mean in D of A, of course. Okay, so this is just another spanning set, and here's the proof. So we know by the work of Mukai from the paper that led to the creation of the term Fourier-Mukai transform that there exists, in fact, an equivalence of derived categories between D of A and the derived category of A dual, where this A hat is just dual abelian variety. And this is not just a random equivalence, it sends pick 0 of A on this side is identified with the set of skyscrapers in this A hat. Since we know that the set of skyscrapers in A hat is a spanning set in D of in its derived category, then using this equivalence, we see that pick 0 forms a spanning set in D of A. All right. So, and in fact, this lemma may be slightly kind of built upon to the following statement, that if Y is a smooth proper variety, then the following are equivalent, the following two properties. The first one is that Y has finite Albanese morphism. And the second property is that pick 0 of y inside d of y is a spanning set. So we have seen that for abelian varieties, the second condition holds, and one may just kind of do just follow the proof using the Albanese morphism to get the equivalence of these two statements. I will not prove this, but it is a relatively straightforward consequence of properties of finite morphisms and the previous lemma. And in fact, this condition that pick 0 of y forms a spanning set is what I need for the proof of the main theorem. Okay, so now I can give the proof of main theorem. So recall the situation. So we have some smooth proper variety y with finite Albanese morphism. And to establish the property that y is stably indecomposable, we need to consider an arbitrary map from curly x to y, where x is smooth proper. And we also need to consider an arbitrary semiorthogonal decomposition of d of x. And we need to show that A is closed under multiplication by arbitrary pullbacks from Y. Okay, so first let's consider, suppose suppose that L is just a line bundle of degree 0 on Y. Then we know that pi star of L certainly lies in pick 0 of X. And here is a statement that actually uses this properness. So here is the part that will kind of break if you want to generalize everything to not necessarily proper varieties. But I don't know, maybe it does not really break, but at least I don't know why it should be true. So there is another theorem by Kawatani and Takawa from the same paper, in fact, that any semiorthogonal decomposition of smooth proper variety curly x is invariant under the action of the group so the connected component of the automorphism group times pick 0 of x on the derived category d of x. So here the action is as follows. If you have some automorphisms of x, we can take pullbacks. If we have some line bundles of degree 0, we can tensor by them. And one can show that these two actions commute. The theorem claims that an arbitrary semiorthogonal decomposition is stable under this action. So this also follows from semi-continuity. And to get kind of semi-continuity to work, we need properness. But I won't speak too much about the proof of this. Somehow the application is that, well, if you have this object pi star L in pick 0 of x, by the theorem of Kawatani and Akawa, A is closed, stable under multiplication by the object pi star L for any L in pick 0 y. since this is just a product by degree 0 line bundle by the theorem, the semiorthogonal decomposition is invariant under this section. So, but now we have established that this semiorthogonal decomposition AB of curly X is preserved under tensor products with many objects, with any object of the form pi star of the pic 0 over here. And it remains to show that stable indecomposability may be checked on an arbitrary spanning set of d of y. So the condition that I have written was that I can take a tensor product with a pullback of any element of d of y, and in fact, it is it follows from definitions that it is enough to check this property on an arbitrary spanning set. And here, this pic 0 forms a spanning set by the previous lemma. And I won't prove this part because it's just application of definitions in the correct order. And with this, we have finished the proof of the main theorem. We have shown that we can multiply A by the pullback of anything in pic 0 of y, and this forms a spanning set. So this in fact holds for an arbitrary, for a pullback of an arbitrary object. So the definition is true. Right. So any questions about the proof of the main theorem?
So can I ask, so in the proof you could already assume that your variety is a Abelian variety, right? But
yeah, that's also possible. Yeah.
It doesn't make it any simpler, right? So you're just proving that Abelian variety is stably indecomposable.
Yeah, it's exactly the same proof. It can be structured as just checking it for Abelian varieties, but I mean, it's fine. All right. Okay, so in the remaining time, I'll just just indicate a couple of applications. Sorry. So some applications, mostly to phantom subcategories. Right. Okay, so I guess I'll state the theorem. Sorry. First, I'll recall a definition that if we have some x which is smooth and proper and some semiorthogonal decomposition AB, then we say that A is a phantom subcategory. If we take the classes of all objects of curly A in K0, we always just get 0. So it's kind of subcategory is called phantom if we cannot detect it using just this K0, this perhaps numerical information. So I think that one needs to know about phantoms is that they exist, but in kind of complicated cases. So this is not precise. What I mean is that we would not expect a phantom to occur in, for example, derived category of the projective space. So I want to state a theorem. Let's say Y is stably indecomposable, variety. And there are kind of two statements. First, suppose that X be a smooth proper variety with no phantoms in D of X. Here I mean that there does not exist a semiorthogonal decomposition where A is a non-zero category with this property. Then the claim is that then no phantoms in the derived category of the product. Okay, sorry, let me finish the statement. So the other statement is if we have pi from X to Y, which is a locally trivial vibration with fibers P1 or P2, then we have no phantoms in D of curly X. So this just kind of confirms the expectation that if we would not expect phantoms in X cross Y because there were no phantoms in X, and this is what going on here. I will not give the proof. I will just say some examples of varieties X for which we know that there are no phantoms. We know that there are no phantoms in, for example, P1. This implies that no phantoms in, let's say, C cross P1, where C is a curve of positive genus. Because whenever we have a curve with positive genus, its Albanese morphism is finite, and therefore it is stably semiorthogonally indecomposable, and we can apply the theorem in our case. And kind of the argument for proving this is basically just applying the definition, at least for the first part. So if we assume that we have some phantom in X cross Y, this means that there is some semiorthogonal decomposition of X cross Y, and we may consider this, we may consider the product map from X cross Y to Y and apply the definition of stable indecomposability to this case. And this uses some general results about linear semiorthogonal decompositions that I won't have time to state, but essentially this is a generalization of this result that I've mentioned, that if Y is stable indecomposable, then any semiorthogonal decomposition of X times Y is induced by the decomposition of X. All right. Good. So, and I guess if there are no questions in the 5 remaining minutes, I can sketch, I can give some generalization of this definition that's more convenient for one more theorem. Other questions so far?
I mean, do you expect any other varieties to be stably indecomposable?
Yes, so this will be, I guess the answer to this question will be what I was going to say. So there is, I guess, some more categorical generalization. So the version of the definition that I can give is the following. So suppose that y is, I don't know, let's say some scheme, doesn't really matter, over this field K algebraically closed and so on. We say that y is non-commutatively stably semiorthogonally indecomposable, which I will always write as n as I for brevity. If a certain analog of the definition is true, if for any choices of two things, first we need some curly D, which is I will explain what this means. It is a perf Y linear category. This is basically kind of a triangulated category with the action of perf Y by tensor product, and this action should be associative. But and that's roughly what it is. But unfortunately, I also need which is proper over Y. And as a classical generator. So those two conditions that I have written are some kind of finiteness conditions, but to make sense of the properness over Y, one unfortunately have to leave this realm of triangulated categories and work with DG categories or infinity categories or something like this, where there is a good notion of properness for categories. But you can just think of this as some finiteness conditions, similar to properness that I had. And second is a semiorthogonal decomposition, which is linear just over a field. So it's kind of the same definition as before, but instead of looking at the derived category of some smooth proper variety mapping to Y, I just have an arbitrary category with this action. So if you recall in the definition of stable indecomposability, from this, I did not use a lot about the morphism from X to Y, outside of the fact that given an object in Y, I can take its pullback and multiply. So some kind of action by the derived category of Y on the derived category of X. And this is categorical generalization. Okay, so the point of this definition is a theorem that in fact has direct geometric implications, that if we have, let's say, phi from Y to B is a flat proper morphism. Sorry, I'm going over time, but I'll finish in a couple of minutes. Suppose that B is an SSI, so this generalization of stable indecomposability. And assume also that all fibers are an SSI. Then I claim this Y, this total space of this fibration, is also an SSI. And explicit corollary of this is if, for example, Y is a bi-elliptic surface, then what we know is that Albanese morphism of Y maps Y to E, which is an elliptic curve. All fibers of these Albanese morphisms are also elliptic curves. I guess I didn't say, but all the theorems that I've stated above for stable indecomposable, they all hold for this non-commutative generalization as well. In the sense that the main theorem is true, that if a variety has finite Albanese morphisms, then it is not only stable indecomposable in this geometric sense, but also in this more categorical sense as well, which is slightly stronger. So this implies that Y is NSSI. In particular, stably indecomposable. So this bielliptic surface is an example of a stably indecomposable variety for which the Albanese morphism is not finite, but in fact a fibration whose fibers are elliptic curves. So there are kind of more examples than just varieties with finite Albanese morphisms, in the sense that if we have this kind of tower of morphisms where both base and fibers are always have finite Albanese morphisms, and the total space is also stably indecomposable. But unfortunately, to prove the theorem, I actually need this categorical generalization, mostly because in this categorical world, we have very convenient and powerful tools to take base change. So kind of what we want to do in the situation would be like to take some point in the base, take the pullback, and kind of do something called the pullback, do something on the base. But if we just assume that the morphism is flat and proper, this doesn't mean that F is always smooth, and there are various complications that we may. Sorry, that's not the only. Sorry, what I mean is that in my definition, if I want to prove something about stable indecomposability of Y, I would need to consider an arbitrary morphism from curly X to Y. And correspondingly, if you want to do some reduction to the fiber, we would have to take the pullback along the embedding of the fiber, but this one is no longer required to be smooth, because this was not a flat morphism. This was, I had no assumption on the morphism from curly X to Y. So when I take a pullback, when I restrict it to this subvariety of Y, I don't get anything nice. But in this non-commutative world, I have a derived base change, which will always be nice. I'm sorry, this is a bit vague, but kind of the proof works roughly as you expect. You just need to have good, powerful statements about how base change works. And that's it. All right, I guess that's all I wanted to say. Thank you for your attention.
Great, thank you very much. Are there more questions?
Ask a quick question for the last theorem. So,
okay.
Do you need to assume that the fibers are smooth to use this definition of NSSI or not?
No, as I stated, I can give this definition of NSSI for any scheme. It turns out that I don't really need smoothness and properness of Y. What I need is to work with categories which are proper over Y and have classical generators. And this is enough.
And for the bielliptic surface case, I'm forgetting. So are all fibers elliptic curves or singular ones, some kind of non-reduced P1s or something like this?
No, so there are two projections, two ways to project Y to an elliptic curve. And one of them is an Albanese morphism where all fibers are smooth. And the other one has some degenerations.
May I ask a question?
Sure.
Oh, yeah. In the original definition, like you're testing for any map from X to this Y. So I'm wondering if you're testing with P1, then does that mean that it has something to do with the like hyperbolicity of the variety Y?
This would be interesting, but I don't really know. So it is true that stable indecomposable varieties don't have any P1s inside. But I don't think I can say anything stronger. Maybe there is a connection with hyperbolicity, but I don't know. Well, that's a very interesting question. Thank you.
So, but the base still has to be a scheme, or is this also a category in your actual theorem?
In this category, is it theorem?
Yeah.
It should be a scheme. This definition of an SSI, one can, instead of looking at schemes, one may perhaps consider an arbitrary monoidal infinity category or something like this. Basically anything for which it makes sense to consider categories with an action of the given one. It's just, I don't know any non-geometric examples.
Other questions? Well, if not, then let's thank Dmitrii again for this great talk.